Welcome to episode 15 in Wireless Future podcast, and I'm here today as always with Eric Larsson. How are you today?
Hi Emil, I'm good. How are you?
I'm fine, and I'm Emil Björnsson as usual, and this time we have a guest, namely Professor Carlo Fischione at KTH, Royal Institute of Technology. He's a professor in Internet of Things, and he's also the chair of something called Emerging Technology Initiative at IEEE on machine learning for communications. Great to have you with us. How are you?
It's very good. Thank you so much. It's really a pleasure. It's exciting to be here. Thank you, really.
So, machine learning for communication is matching very much with one of the previous episodes that we have in this podcast. However, I was planning today we will turn it around and talk with something that you also have been working on, namely how wireless communication can support machine learning. So rather than communication for machine learning. So to get things going, what is, in your opinion, machine learning?
That's a very good question, and there is actually not a scientific consensus on the precise definition of machine learning. But generally, in the areas that are interested for us, that we work with normally, I mean wireless communications and related areas. Normally, with machine learning, we intend the fact that we have certain data, and we would like to associate a meaning to this data. And this association is therefore a mapping. So a mapping between data and labels, the meaning. And so it's, in a nutshell, we can say that machine learning it's finding this automatic mapping between data and what they mean. And it's interesting that machine learning in this regard is seen as a subset of artificial intelligence, a little bit more general area from many point of views, but also this is debated, and people have proposed even a more general name that includes both artificial intelligence and machine learning, and this is the data science. So that's we are therefore working in this kind of larger domain that today is generally called data science.
So if we just look at conventional algorithms that also might take a measurement of some kind and then make a decision, say we are measuring the quality of a communication channel and then we determine what power we should use or something like that. What makes machine learning based algorithms different from conventional ones?
Yeah, the main difference is that in conventional algorithms that we have been using so far, usually we work with analytical functions or with analytical arguments, and this means that if there is the data and we have to take some decision based on the data, such as performing handover in wireless communications, or adapting the transmit rate, or deciding which modulation format. All this has been done now quite successfully, by the way, with sort of algorithms that are built with analytical arguments, where one has a model of the physics that is happening, wireless, the way the waves are transmitted over the wireless channel, a description of the fadings in analytical terms. And so the algorithms are, in a sense, is a result of calculus, in the basic calculus, if I can say now in a very rough manner. And instead, machine learning has another approach here, where these algorithms are not based on a series of logic steps and proofs, but rather it's more an empirical, if I can say so, an empirical approach, and where the algorithms are built on experience. To give a more tangible example of this, we can look to, for example, the Shannon capacity that, as we all know, is an analytical relation between the signal-to-noise ratio and the achievable data rate that a channel can successfully support. And Shannon, one of the great scientists in our research areas, he derived the Shannon capacity and with analytical arguments, working, by the way, for something like 10 years, and using ideas from calculus and algebra. And this equation can be seen really as a function that takes as input the signal-to-noise ratio and gives as output the data rate that a channel can reliably support. This is, in a sense, is what is done traditionally in our research area. In wireless communications. But now machine learning, data science is offering an alternative approach in which this map between, in this case, signal-to-noise ratio and achievable rate is derived empirically, looking at many experiments and then trying to generalize in an empirical manner the association between signal-to-noise ratio and achievable data rate. And now this is creating a series of new interesting questions and possibility. But I think that is also interesting for us somehow to remember that in the history of science, in the history of research, these ways of approaching problems is not new, and is almost in the beginning of the modern way we intend science. In the 1600s, the astronomers, they were looking at the motion of the planets, recording really where is the planet right now, and looking at the sequence of data, and then out of these recordings they try to generalize the way the planet were moving. This was the approach of Tycho Brahe. Since we are here in Scandinavia, here was a Scandinavian, well-known Scandinavian astronomer in the 1600s. Then the century after, Isaac Newton somehow arrived at the same conclusion, but with analytical arguments, I mean geometrical and calculus-based arguments. So it's, in a sense, it's two different approaches, one analytical based, the other one data based, and they are not at all in contradictions. They go wonderfully together, and one inspires the other, one is needed for the other. And so we hope that this is going to happen in wireless communications.
Yeah, I think this is a great way of describing it, that sort of all our models are from the beginning based on people who made measurement, collected data, and then tried to explain the phenomena using models. And now the question is, when we are developing new algorithms, should we base it on the good models that we know already, or should we use new data from which we haven't extracted model yet, or which it's very challenging to extract models?
Yes, that's a really an important question, and I believe that in many cases we will be using our model-based approach, our analytical approach, and in other cases, when we have lots of uncertainties and complexity, then probably the data-based approach could be more useful, more performing.
Yeah, it's quite fascinating. So, Carlo, you have written this paper, Wireless for Machine Learning, and in this paper you talk about the notion of, on one hand, centralized machine learning, and on the other hand, decentralized or distributed machine learning. What are the differences really here between centralized and distributed, and what are the use cases for these different approaches?
So it's these algorithms, centralized and distributed, they have a different nature, and can also be used for the same approach. But in general, the basic difference is that in machine learning we have two elements that we have to keep in mind, and one is the data, of course, and another element is the computation that it's to build the mapping function from the data to what they mean. This is one computation, and then another computation that is about once we have built or computed the mapping function, then we have to use this mapping function that will take as input new data and will predict, will tell what is the meaning of the data. So the first kind of computation is called training, and the second kind of computation, it's generally, let's call it inference. Now in centralized and distributed machine learning, data, training and inference could happen in a different manner. And in particular, in centralized machine learning, the assumption is that all the data is collected in some central location. And in that location, we also have all the computational power that will build the mapping function, and that we will also apply this mapping function to make the predictions, to make inference. Instead, in distributed machine learning, we can have this strange situation in which some data is here, some data is there, and some piece of the computation for training is done here, some piece of the computation for training to build the mapping function is done there, and analogously, once we have built the mapping function, we could have a piece of computation here to make the inference, another piece of computation there to make the inference. So generally we can say that in distributed machine learning, data and computations are spread. And this is actually the case of wireless networks. This is certainly the case of wireless Internet of Things. And I believe that one of the most important current revolution that we are witnessing today is the revolution of the Internet of Things, where many wireless devices are embedded in whatever. It's in our buildings, inside the human bodies, in the cities, in the smart cities, in the environment, on the lakes, underground. So it's thousands and thousands of wireless devices. And in 5G, for example, we speak already of the order of 50,000 wireless devices per square kilometer. And I'm speaking of wireless devices that are small, not our smartphones. I'm speaking of really wireless sensor devices for environmental monitoring, city monitoring, traffic monitoring. And this will be added to the smartphones, to our laptop. So it's a huge, enormous amount of devices that are distributed over relatively large geographic areas. And so this is it's a natural situation in which computations and data is distributed. And in these cases, we have a whole set of new services and data analysis problems that are different from doing data analysis in a central location. There is many examples that we can do here for this distributed machine learning. And one of the simplest is that we would like to predict where is, for example, the traffic flows, the vehicular traffic flows in the cities, putting together measurements from camera sensors, noise sensors, and these predictions have to be done in a relatively small local geographic area. So this is demanding for distributed machine learning services and algorithms and methods. And that also every time we are working with the data that have a form of privacy and security, we necessarily will have to do distributed machine learning, such as if you wish to know what is our health state, let's say, and we have wireless sensors in our body that are collecting measurements, then this data has to be analyzed locally, and the prediction on our health state has to be done locally, distributed. But at the same time, for making these predictions and to make a successful data analysis, we have to use in some form, in some manner, data also from many other people and from other data sets. So we need a form of distributed computations that are respectful of privacy and security and many such issues.
All right, Carlo, so what you're saying is that with centralized machine learning, the learning model resides in a central location, and all the computation happens there, and all the training data are fed there in order to facilitate the learning. Whereas with decentralized learning, then training data might reside at different distributed places, and some of the computation also happens distributed, so that there is no need to like aggregate all the training data to a central location. Oh, that's interesting. Emil, do you want to continue on this line?
Yeah, I started to wonder. I've heard about the concept of federated learning, but I'm not entirely sure what it is. Is this an example of distributed machine learning?
It is, yes. So it's now federated learning is one method that it's very popular, and one of the reasons of its popularity is that it's actually used in our smartphones. And it's a typical instance, it's a typical example of distributed machine learning, where the problem is that every wireless device wants to have a good mapping function from the data to labels. This is called this mapping here is called model, and to compute such model, one not only needs the data stored in the local smartphone, in the local wireless device, but also data in many other wireless devices. And federated learning avoids to exchange data. Instead, federated learning exchanges some temporary models, some temporary mappings, and in a star network topology. This, after a while, with iterative computations, arrives to very good computation of the mapping function locally at our smartphones. And yes, as you say, that this is an example of distributed machine learning, but there is very many other cases, very many other examples that are quite different from federated learning. And interestingly, if we look at the research in the area of parallel and distributed computation, we have, among others, a very famous book from 1987 of Professor Tsitsiklis from MIT, and in this book we can say that federated learning is one of, I don't know, a few thousand possible examples of distributed computations, distributed methods that we can use. And there is many more methods. I mean, federated learning, it's when all the wireless devices are more or less interested to computing the same and common mapping function, the same common model. But we can have the situations where the models have to be different. Still, the device needs forms of exchanging data, because the computation of the models depend on the data of the others. And then we have the even more challenging situation in which data are it's unequally distributed among the devices, and the features of this data in particular is unequal distributed. And here we would need entirely new methods. So in particular, in the case where the models are different, there is one of the well-known methods, very different from federated learning, is called COCOA. Just to give now to name one of, so that yes, federated learning is a prominent, very popular method, but is one of the very many methods that we need in distributed machine learning.
So if we just stay on federated learning or related methods, is the reason to not send the all of the data, all the observations up to some point, or to share them between the points, is the reason for that to protect privacy, or is it to reduce the amount of signaling, or perhaps a combination?
Yes, it's actually, as you said, Emily, it's a combination of all these issues. One of the characteristics of almost all distributed machine learning methods, and therefore also federated learning, is that what is sent from the wireless devices to a sort of cluster head, a sort of coordination point, is not raw data, but some transformation of this data, then this transformation can ensure up to a certain level privacy, because data is not sent plainly, but there is some algebraic manipulation that is done, and this increases the level of privacy. At the same time, all these distributed machine learning methods doing this local processing, local manipulations on the data, they have also the potentiality to reduce the amount of data to transmit. And so this is very good, especially for our wireless, for smartphones, Internet of Things, because to send a huge amount of data, it means to use energy from the batteries, and if we can reduce the amount of data to transmit, then the batteries last longer, and everything is much more energy efficient. This is not always obvious that we reduce data, but in many situations we can do this. We can really do a huge data compression, a huge data reduction with methods such as federated learning or many other distributed machine learning methods. It's also interesting that yes, we reduce privacy in sending these transformations of data, these algebraic manipulations, but again, this is quite dependent from case to case, because a listener who could be there and could collect these transformations of the data that are sent over some communication channel, this observer could reconstruct pieces and bits together, and can in some cases still be able to uncover the original data. So yes, distributed machine learning methods can increase privacy, but it's not obvious, and it's not always the case.
Yeah, and then I guess this distributed method could also be run over the wired part of the internet. But if I understood correctly, the aspect of wireless here is particularly that the devices are wirelessly connected or battery powered, and that we need to take those properties into account.
Yes, this is a very good point that you are touching. I mean, now that of course, it's as wireless researchers, we are interested to this domain and its method and the technological implications, and all distributed machine learning methods. There is a relatively long research history that goes back at least to 30 years, and all these methods they have been deployed having in mind not actually wireless devices or wireless networks, but rather networks of servers. Such as in data centers, there is a number of distributed servers, because every server doesn't have enough memory or enough computation to process the huge amount of data. And so there already 30 years ago, 40 years ago, researchers, especially in the area of parallel distributed processing, they came up with the idea of distributed machine learning. But now what is happening again in this revolution that arguably we are living today of the Internet of Things, data is generated in distributed devices, wireless devices, and the methods of distributed machine learning that come from the world of parallel distributed computing are not good enough for wireless situations because of the communication channels are not those communication channels in the data centers. There in the data centers there is powerful optical cables that connect servers, but we know that in wireless communications the channels behave quite in a different manner. And so the exciting somehow news for research in this domain is that we need this federated learning method, more in general distributed machine learning method, have to be re-engineered, redesigned, sometimes even from the beginning, for wireless networks, for wireless world.
So Carlo, yeah, I mean, speaking of federated learning and the transmission of, let's say, learning model updates over a wireless interface, are current wireless networks and standards appropriately designed for this application? I mean, it seems to me to be like an entirely new application of wireless, right, to send model updates in fed learning. Are current networks and standards appropriately designed for this new application?
So somehow the sad answer is that only partially, and this is sad because then the development and the usage of machine learning and related services is somehow hindered from the current communication networks, in particular public wireless networks such as 4G and 5G. But at the same time, this is an exciting news because we will need to redesign and to advance future wireless networks to support this kind of services. They are more in general services in the area of distributed intelligence. And so it's many, including me, think that wireless communication protocols, the existing wireless communication protocols, are not intended, they are not optimized for machine learning. And what does it mean this in practice? It means that if we try to use these communication protocols to support federated learning or in general distributed machine learning, then either we will get poor performance or we will not get the machine learning tasks done on time and with the efficiency that we need. So we need to really, many, including me, think that we really need to redesign and conceive an entirely new set of communication protocols, wireless communication protocols, to support machine learning services.
Yeah, it's quite exciting. So, but how about, for example, in 5G, there is this notion of network slicing, I think. Is that anything that could be exploited for machine learning and federated learning in particular?
Oh, definitely. That's now one of the somehow revolutionary concepts in 5G, that the network can be parted in slices, and every slice can be associated to a specific service. And so hopefully there will be one day in the future a slice that is associated to machine learning services. And this is something that likely we will do relatively soon, but then we will realize that the slice using current 5G technology is still is not good enough for the range of machine learning and more in general artificial intelligence services that will have to run on top of wireless networks. But that's really the concept of slicing. It helps, and historically, again, we can see an interesting trend that in the history, or if you look at really at the last 120 years of radio communications, we see that radio was first developed just to send some basic signals. Then it evolved to at some point to send voice communication with the diffusion of radio, thanks to the Irish-Italian inventor Marconi. Then later on, it was further developed to send data. I mean, data that not necessarily had to be sent in some form of real time. Then we had later on in the 1980s and multimedia, 90s, multimedia communications. Every time there has been a technological evolution introducing specialized communication protocols over wireless, and so that will be now. This is the decade of the artificial intelligence and the Internet of Things, and so I believe, as many others, that we will need dedicated slices, dedicated new protocols to support artificial intelligence.
Yeah, very nice. Emil, do you want to follow up?
Yeah, no, I think this is a great point. Sort of, I think network slicing concept was also designed for technology to be forward compatible, and maybe when it was designed, the idea was that the first slice will be broadband connectivity, then we will have low latency, robust communication, and IoT device just for sending small data. But potentially this machine learning type of slice might be something that will be much more important than not mobile broadband perhaps, but the other two, because everyone have a device with a neural engine in their iPhones or so there will be plenty of data to transmit. So let me switch topic a little bit and ask you about something else you're talking about in your article, Wireless for Machine Learning, over-the-air computation. That sounds like a new exciting direction. What is that?
Yes, no, that's now actually very well connected precisely to what we were speaking about. So we just say that luckily, arguably, as somehow researchers here and engineers in the field, we feel that wireless communications are not well performing to support artificial intelligence, to support machine learning. And the reason is that historically, wireless communications they have been developed with the ideas to send some form of data, voice, video, multimedia, not machine learning, not artificial intelligence. And now over-the-air computation is, if I can say so, a groundbreaking new idea that proposes to send information for distributed computation. So on their function computation uses the concept that if different transmitters are transmitting at the same time and at the same frequency, then the electromagnetic waves, the radio waves, they can overlap at a point at the receiver. And this is a perfectly, a very natural concept. Is that if many people are speaking at the same time, a listener will hear their voice superimposed to each other, overlapping. And so is with wireless, with the radio waves. And now that this overlapping of radio waves in traditional communication systems up to now generates interference, and essentially we can say that wireless communication protocols up to now have been built considering interference as a strong enemy, as something to avoid as much as possible, and all the techniques are there to counteract interference. But, and this is now the groundbreaking concept, in distributed computation situations, such as in distributed machine learning, interference is not any longer an enemy, it's actually can be a friend, because interference or overlapping of simultaneous transmissions is a computation, is a sum, and this sum now can magically make for us computations as we are transmitting data or transformation of this data over wireless communication. They can be summed up over the air, and this is really something that has been noted relatively recently, and is approximately 15 years ago that there is some small papers that have been trying to work with this concept, and maybe one day it will develop in its full power, which means that the wireless communication will become an analog computer that performs a computation for us without that we need a third party or a third place where these computations are performed. And again, looking historically here, if this idea of over-the-air computations for artificial intelligence, for machine learning, if this will be true one day, in maybe 20 years from now, 15 years from now, then historically we can see an interesting perspective that we have had the cloud computing. All the computations are done somewhere in servers on the cloud. Then we had the concept of edge computing, where the computations are done close to the base stations. And then we had the concept of fog computing, where computations are done even closer to the wireless devices in the wireless access points, which would then be connected to base stations. And if these on-the-air function computations will be successful, then we will have clear sky computations, so that we will forget about a little bit fog, edge, cloud computing, and the computing will happen magically over wireless communications.
This is an exciting idea. So I think when we talked a few episodes about cell-free or distributed MIMO system, that was sort of about sending the same signal from multiple places and make them add up constructively over there. But here is rather to send different data that only exists at different locations and then let them add up over there. So what do you say, Eric?
Yeah, I mean, over-the-air computation is really like, I mean, you're exploiting the superposition principle of the wireless MAC channel, right? I mean, it's like NOMA in the analog domain somehow. So it's pretty cool. I'd also imagine, I mean, that this brings with it a number of new challenges. Like, for example, if you want the signals to add up synchronously, then number one, you need appropriate power control. Number two, you need phase synchronicity and so forth. Do you want to elaborate a little bit on that, Carlo, on the challenges here in making this work in practice?
Yes, Eric, this is really now an interesting set of questions, and this idea of their functional computation, we can say that it has been observed at the level of a principle, and in the technological scale of readiness of a service or product. We know there is 9 levels, the technological readiness levels. And I think over-the-air functional computation here is at the level now maybe 1 or 2. It will take so much more research from scientists and engineers to evolve it to the point that will be practical. Because as you said, there is many still questions to solve. First of all, as it is conceived now, we need that all the involved wireless devices have to have a very fine time synchronizations of the order of nanoseconds. So it's really, really fine synchronizations that could be complicated to achieve. The other big problem is that all the devices need to have a very good estimation of the wireless channels from where they transmit until where information is received. And this has to be very good estimation. Otherwise, these computations over there are greatly affected by this kind of error. Then there is also the question that the modulation that we have used to use the physical layer of the isOSI stack, this modulation are special. They are specially intended for over-the-air function computations, and is not always compatible, this kind of modulation, for example, with the current 5G standards. So new modulations here also means a new hardware, new kind of hardware that we'll have to use to make this principle technologically possible. And then we have all a series of, so to say, foundational questions about the ultimate complexity and performance of these over-the-air algorithms. So all this will demand really 10 years, 15 years of hard work of many bright researchers all over the world.
Yeah, this is exciting. I mean, it's great news for everyone working on wireless physical layer and MAC layer design, I guess, as well. Emil, do you want to talk about
yes, I
something
was,
new? Yeah.
When I was reading your article, there were a number of other things that catch my eyes, and one of the things you mentioned is importance-aware communication. And then first when I saw the title, I was thinking that, in communication we have all of the source coding where you sort of look, okay, this is the content that we're going to transmit, and then we are using its entropy. If there's high entropy in something, well, with them there is more importance in that information. It's less easy to predict it, so therefore we need to send more bits to describe it. And then there's the other way around, when the information is sort of already more or less known what it's going to be, it's easy to convey it. And but it seems like this is something different. It's some other kind of importance of the content that you are capturing within importance-aware communications.
Yes, that's indeed. There is various similarities, and but at the current state of research, this line has not yet been explored. And what are the similarities, and what are the concepts? The concept is that when we transmit let's again as reference federated learning as one of the many examples of distributed machine learning. In federated learning, we have to transmit from the wireless devices to some central point. We have to transmit the models, the local models, or the so-called, now to be a little bit more technical, the gradients on the loss functions that are computed on the local devices. And what is extremely interesting here is that these gradients are it's a vector, and we might not need to send all the elements of this vector. We don't need to send over wireless communication all the elements of this vector, because for the computations of distributed machine learning, it could be that the elements of the gradient vector, they don't bring particular importance. These elements have of some reduced magnitude, or they, in some cases, they even introduce noises in these computations, even over-the-air computation. So the concept is that we could, instead of sending the overall vector of the gradient, that could be in many machine learning cases, this vector could have millions of elements. Say that we can reduce 99.9% of this million of elements of the vector of the gradient. We have a tremendous saving from a wireless point of view in terms of usage of wireless resources and the transmit powers and occupation of the channels and so on. But now what is here interesting is that the way we reduce the elements of this gradient vector, the way that we have been using so far is grounded on optimization theory ideas, and such as looking at the noise that the removal of these elements of the vector generates where the computation is performed, and looking at what is the minimum level of noise that we can achieve in these computations. And then having in mind this optimization point of view, this error minimization point of view, we could decide to remove more or less elements of the vector, or we could decide to do a quantization of the element of the vector, because quantizing with a rough quantization we save lots of bits. Or we remove some of the elements, or we could even do what it's called sparsification. Sparsification is an operation in which we intelligently compress a vector to a smaller vector thanks to an underlying property that the original vector has, and this without causing too much information loss. Now, all these ideas have been analyzing, having in mind minimization of errors, which is in the end estimation theory, optimization theory. And now you asked, Eric and Emil, you asked why don't this reminds us information theory? That's a fantastic question. Maybe we should write a paper on this. People have not yet done. And in fact, if we think to estimation error, the estimation error in an estimator is connected to the Fischione information matrix, and so there, the branch with information theory is immediate. So that could be next paper on the subject.
I see. Yeah, so I think one of the big use cases of machine learning in general is to say, take all these optimization algorithms that we know are asymptotically converge into the optimal decision or optimum of some kind, and then we try to either make them converge faster using machine learning to tweak the algorithms, or in this case I understand it's like you try to reduce the amount of signaling. So instead of taking the best step in your algorithm based on optimization theory, you say, okay, I have a certain budget of information I can send, so I would like to utilize this information budget to take as many good steps as possible.
Definitely, and this is so well connected to what we were saying before, that distributed machine learning has been somehow considered and invented for the world of distributed servers, but now when we are doing wireless communications, we have to re-engineer it. We have to do something different that is good, not only to achieve the training functions at some point, but also is good for the wireless devices. We don't want that our wireless device die after 10 minutes of doing some AI service. And that's here is the excitement of redoing these things together, wireless and machine learning together.
Yeah, it's amazing. I mean, there are so many new and interesting and exciting research questions here that are emerging. So I think a final topic that Emil and I would like to touch upon here in the conversation with you is on privacy and security aspects. And we already mentioned, I think you mentioned, Carlo, privacy aspects of federated learning, where there's always a chance that even though an agent or a device has its own training data and doesn't share the training data, but just performs model updates on that data, that the update itself will leak some information, right? And if I understand well, the technical term for that is deep gradient leakage. But there's also, I would imagine, a host of security aspects of distributed machine learning, and especially where the updates are sent over a wireless interface. For example, one could think of jamming attacks, where some hostile device transmits all sorts of junk, okay, meant to destroy the communication link. I'm not sure to what extent there would be much or any different from jamming attacks in say, conventional wireless applications. And on top of that, I believe that there are also poisoning attacks where agents intentionally misbehave in order to cause damage to the learning model by sending, well, gradient updates that just pull the model into some entirely wrong direction. Do you want to elaborate a little bit on this, Carlo?
Yeah, that's really a fantastic set of questions here, and it's an incredibly complex research. First of all, the notion of privacy, secrecy, security is very complex on its own, and there is even different disciplines that work together, that have to work together here to arrive at some point in the future to some answer. And just to give an idea of this tremendous research complexity, we have the notion of cryptography, we have the notion of differential privacy, we have the notion of information theoretic secrecy, and then the notion of multi-party computations. And I myself a few years ago suggested the idea of optimization theory-based privacy. It's not always common what is it's not always clear what is the common element among these different notions, and then how to embed by design privacy and security properties into distributed machine learning over wireless. This is really almost unexplored, and one needs many years of research and investigation. And as it is at the state of the art here, the situation it doesn't look good, in the sense that it's easy to for a wireless device to start to inject wrong data, or to participate to some distributed computation with the purpose of destroying these computations. So it's yes, it's many questions to investigate.
Right. I mean, concerning the latter, I mean, a device that just injects some false data, how can you even tell, right? How could you even distinguish between an agent that is intentionally misbehaving and injecting some junk data or sending some junk updates to the model from an agent who has access to some unique and genuinely valuable training data? I mean, if you are, like you have a network of cameras, and almost all the cameras see a street view with people walking, but one of the cameras see an elephant walking on the highway. How could you tell then whether this camera is misbehaving and intentionally trying to fool the learning model, or whether it really observed something which is highly important for the network and for the model to know about? So I suspect there are like a host of new questions that emerge here, and which are absolutely non-trivial, and which would require knowledge and approaches from multiple disciplines in order to address.
Definitely, that is exactly the central consideration here, and it's a difficult questions, it's new questions, interdisciplinary questions. And really so much exciting research is needed. So it's really the case that security and privacy for distributed machine learning, for distributed artificial intelligence is at the infancy, together with also many of the considerations that we have done so far. So, and this for us researchers is good news.
Absolutely.
Yeah, no, we are delighted to have you as a guest in this episode to talk on the theme of wireless for machine learning. And thank you very much for sparing some of your time with us. And in the description of this podcast, you will also find a link to the paper. And we'll also put a link to your website and to the this ETI, IEEE Machine Learning for Communication Emerging Technology Initiative, which I think people who are interested in the topic could find a lot of interesting material there as well.
I agree. This was a great fun conversation, and I learned a lot as always. So thank you very much, Carlo, and thank you, Emil.
Thank you so much, Emil and Eric. It was a great pleasure to be here. It's really fantastic. Thank you so much.
And thank you to listeners, and we see you in the next episode. Bye-bye.